All right, so we plug in the adapter here, and now we're going to do another ls mod and list all the features of the kernel. And it should be a different list than it was before. Well, if we do it almost immediately, then the kernel may not have noticed and got them options loaded. But wait a little bit, and then do the ls mod command. And you should see something different coming up. Now, again, these things got put into files, so you don't see anything at all. By the way, when I grade the scripts, I'll be looking to find these files, and you'll see these on correct. All right, but if you do a diff here, you'll see that a few lines have changed in the lists. In particular, there would be this keyspan guy that's in. And there's some stuff that depends, that keyspan depends on, that also have to be added. There's a USB core, I believe, and one other guy that's you'll find that's different. So expect about 3 different lines to be different. And the lines you get are going to have like a module name here, and then some numbers, and that refers to how big this piece of code was that we put into memory. And then who cares about it is what we would have out here. So when we load in that USB core thing here, it's going to say, hey, I loaded that in because it's being used by this keyspan module. So that's what you get out of it. All right, now as you make these changes, the kernel keeps track of every little thing that's changed on the system. Look at the last 30 lines in var log messages, and it will tell you, hey, I'm adding these modules and things. So take a look at that and get an idea of what sort of things get reported. It's very similar to the kind of things that got reported when we first do a boot up, right? If you get out of that stupid little green screen and watch the actual line-by-line things go past. That's the kind of things you can find in the messages. It's well beyond the one that we actually wrote. All right, so where is this stuff? Again, we've got a update DB command to update the locate database, and then the locate guy will browse through that database. Let's find all the guys that have the word keyspan on the system right now. This is the stuff, since you didn't put anything there, that got sucked off the disk drive. And in particular, we'll see some things like this. Under lib modules here, there's a subdirectory for each of the different kernels that we might have on the system. Different kernels can have different modules that get glued on. If you have a different guy, you want to glue somebody else's module on. So they have to separate all these guys out. And indeed, we're going way down into subsystems here, into the driver subsystem. This is for an input device rather than output device or whatever. And it doesn't fit any particularly good category, so they put it under the miscellaneous thing. And we have a few guys here, like keyspan PDA, keyspan remote, which doesn't really concern us. But this is the one that is used for this particular device. All right. And then also, since we told it to give us the source for building the kernel, all the .c and .h files and make files and whatever that we need to build the kernel, we'll also find it mentioned in a few other places. There's a keyspan.h and a keyspan.c under user source. And again, we can have lots of different directories here if you have source for different versions of the kernel. We probably only have one in our system here since we didn't go out and update things when that disk was created. All right, but often if you have your own system at home, right, and you're doing updates on your Linux systems and whatever, every now and then we'll bring down your kernel and we'll bring down another big pile of these guys here and put some more stuff in your root directory and so on. You can see a little bit later on. Okay. All right, so the kernel object that we just glued on here as a result of plugging in that device, that's underneath the modules. Source, that's going to be able to create these modules later on, is under the source. And we sort of borrowed this name, you may recall. We had a user local source where we were putting our CTWM stuff in. This is the user source for the stuff that the distribution is providing us, rather than new add-ons. All right, so now you can not to do any uncounting or anything like out with this little device here. It's not like a flash drive or whatever, so you really can't just unplug it and when you're done. So unplug it and then give it a little moment to see if it's going to do anything, and then take another rest. But you should find this time it didn't do anything. We loaded those modules in, but there's no provisions for removing those modules once you're no longer using the device. So our kernel is right now a little bit bigger than it needs to be. We use something else on the side of it that doesn't involve the device that's there. All right. Now we can try to remove those modules to give us a little bit of our RAM back. The kernel itself is in memory and it stays in memory. It doesn't get swapped out or anything like that. It stays in memory essentially all the time. So it pays to try to keep our kernel as small as possible so that there's as much RAM as possible for the user programs that we're running. So if you have stuff that you're not needing, it's best to either, well, of course, don't load them to begin with at all, and take them back out when you're not using them. So we give it a try to do that. Now, I don't believe this is happening in CZ12.2, but in previous versions of this course here, back when we were using CZ11.1, we actually were able to hang up the system at times when trying to do these removes. So I've given you kind of a safe way to go about doing it, although I don't think it's actually necessary. But again, it's a good opportunity to talk about what the safe ways of doing it. All right, so if you do get sort of stuck in a system call here, and when it's coming up here, we try to remove things with the RM mod coming up. You can't do what you normally do when a program hangs up on you. The Control Z to stop it momentarily, or Control C to try to kill it, because you don't have control of your shell at this point. If your shell did this system call here, nothing's going to happen until the system call is complete. All right, so there's no good way around it. So what we do instead is put it in the background. So that makes a separate job, and if that thing gets hung, well, we don't care all that much, as long as we don't put it back in the foreground. It'll be fun. All right, so you can try to remove it here and then do an ls mod again and see if the word keyspan has showed up. Right, so if we've done it right, if that guy succeeded, then we would see those three entries that you had found back here when you did the diff. USB 4 and a few other things here, but there was one guy that mentioned keyspan. Right. All right, now, by the way, if we had left the keyspan thing plugged in and tried to remove the module while the device was still being noticed and used by the system, bad things tend to happen. So you really don't want to just yank out some modules that might still be used. So again, all right, now we're going to discuss the different ways to put these guys in. We've already seen one, sort of by magic, these extra modules showed up by us doing nothing other than changing hardware on the fly. Okay. All right, so the system looks for things, you stuff in the USB thing or compares it to a list of what might handle that. If it finds something, it will try to load it for you. And that, as it turns out, works out most of the time, but occasionally you may have to do things on your own. One command, kind of like the RM mod, is the ins mod for insert a module. Okay. So we could indeed try to do that. We could try to remove the module for USB serial. And then try to insert it again. Try to load, for example, the keyspan. The earlier list told us that keyspan requires that module to be loaded if it's going to work. It's expected to be able to call some routines and whatever that are that part of the kernel that's supposed to get moved on. And we remove that portion of the kernel at this point. So it's not there. Now, if you do try to go ahead and do the insert mod thing here, notice it's a little bit annoying because you have to find out the whole manual path of where that thing lives, first of all. Now you do that fairly easy, of course, by go /lib/MO tab will probably complete it. Give it the first part of your path name and a tab and complete it itself. So you get there fairly easy without typing every single character along the way. But if you do that, it should tell you, hey, I can't do that. I was expecting to find this symbol in the kernel somewhere, and it's not there, so I don't know what to do with it, so I'm not loading this device because it's not going to work. All right, so you see something like that right there on the command line. Again, look at the bottom of var messages, and you'll see there will be those complaints about what's going on. All right, so it's telling you there's some stuff that it doesn't know about. It's a pretty good idea of what that is. We remove that other module, which apparently is crucial, so one we're assuming that if you remove that guy, everything will be okay. And indeed, if you do that, control P or whatever, you get back to almost the previous one. Control W, you get you back to the slash, and then start typing the USB stuff and put that in. So load that module, and then try to load that one, and presumably you will get that error. So that pretty much confirms our suspicion that the symbol that is needed is something that was in this kernel. And now that that's actually attached to the kernel, we don't have the problem. All right. And then doing LS mod, we should find those 3 guys that we've seen before still reloading. Alright, so notice we did that without actually plugging in the device. Right? We can tell it to load things that we aren't really needing to do that as long as you keep the interaction working. Okay. Alright, now there's another way, that's sort of like a long clunky way of doing it. Generally, when you have a choice, you don't want to use that one. So you use that if you very explicitly have something that you want to do and make sure that it doesn't do it in the wrong way. But usually, besides the magic. So let's once again try to get rid of some things. And notice if we try to get rid of the serial guy, it won't take that out. The key span is already in there. It's not going to yank this out and leave the key span thing broken without having the symbols that it needs to reference it. So we just won't let you do that. We say, hey, this is used by some other guys, and that means we'll give you a list of them here, so you got to make those guys go away first. So if you do it this way, remove the key span guy and then the USB serial, then you would get the control. It should let you do that. All right, and if you want, do an ls mod there and grep for key span to make sure they really did go away. But again, if you didn't get complaints here, then she really did. All right, so we can do we now load these things quite easily here by using the mod probe command. And notice I don't have to give it a big long path name. I don't have to put the .ko on the end of it. I just give it the name of the module I want to work with. And it'll take care of that. And it will notice along the way that, hey, for this thing to work, it needs USB serial, so it will also do that one for you. So you not only don't need long path names, you don't have to know all the dependencies. It will generally take care of that. All right, so do that, you should find that your span stuff is back there. Okay. All right, so next up, we're going to try to build a new kernel, and that's underneath user source. We're going to go to the Linux distribution here, and that's generally a soft one. So there's some big long name in there, Linux doc whatever, with a whole bunch of numbers and dots and whatever for a particular version here. And this guy points at essentially, the one we're using now, the most recent one. That's probably the one and only one that we've got on Susan from the installation. So we're going to go down into that little disk here, and you can do an ls and see all the different subdirectories and things that are around. And in order to build a kernel, what it means is a configuration file called .config. You do the -a option here so that you can see things, and there probably isn't a .config there just yet. So it may have a make file, and this guy here is in charge of making a whole bunch of other make files and otherwise making lots and lots of different parts. Now, before we get too far into that, it's probably worthwhile to talk a little bit about make files, just in case you people aren't used to dealing with these things yet. So I got one here from the operating system course here. If you care about looking at this one, you can find it underneath the tilde CS470 directory in 3 subdirectories. Alright, so it has syntax essentially like this. Pound signs here are comment lines. You can define various variables here, and the two most common things for CC to be is either plain old CC or GCC. And you can set up whatever flags you want to be given to the C compiler. So you may recall from other courses with the -G flag, this compiles it and leaves the symbol table in place so that you can run a debugger. And that way you can say, show me what's in variable I, and it knows what you're talking about. We'll be able to figure out what the address of where I is stored at, and we'll get those bytes and show it to you as a baseline number. Now, the particular thing I was doing here in P3, it wasn't going to be enough to say GCC my .c files here. I needed a whole bunch of other options to be set up. So that's what the rest of this stuff is. These are going to be the default options that get used anytime I use the GCC command. Now, in general, the way standards are set up in a make file, you have basically a target name here, the name of some target like test or P3 or P3 name.o or whatever. And then out here, you have a list of dependencies. And then some lines after that, these are tabs here. And so a bunch of spaces doesn't work, it really has to be a tab here. And then what we have out here are commands to make that target. And as it mentions in the file there, our first target is called test. So if I say make test, it's going to do basically what it says here. It's going to run P3 in this particular directory with a parameter of 37. But test depends on having a P3 binary available to work with. So what it does is it checks here to see if this thing is up to date. And the test is not a real file in this directory at all, so it's always going to be considered out of date. So you can make sure that P3 had actually gotten made. And that's what this thing is here. Another target, here's how you make P3. You do this command down, which is actually the way you're going to get it. And we have dependencies here. You shouldn't be putting together the .o files until you check that P3 main.o is up to speed and P3 helper.o is up to speed. So if it turns out that we have a P3 that was made yesterday, but a P3 main.o that was made today, that means this guy's out of date, and I need to recompile and put together the .o options again, and make a new version of P3 using the new object. Okay. And since this is kind of a complicated program here, I need to say more than just run the loader or GCC here. I have to tell about other libraries that it's going to use. So these are the options that we're going to look at. So we're going to tell, instead of calling the thing a.out, we're going to use that O option and rename it to 3. And we're going to put together these .o modules all in one big package. Plus, pulling out some stuff, some references to these other libraries. Right, now, where would the main .o come from? Well, the main file is the dependencies here. to get a let's call it name, just bring our name down. If that's your target there, it knows already. You don't have to write out your name.c. If you change your .c code, then the object module is obviously out of date and would need to be remade. But make doesn't require you to put in all these obvious things. If you're one of these guys, it knows that you better go figure out where P3 helper.c is and make sure that's up to date. So there's some implied dependencies out here that you don't have to list. On the other hand, if, as it turns out, our P3 name.c includes P3.h here, which has some definitions in it, there's some constants in whatever. And if we changed any of those, then the wrong constants are in P3.o. So I have to tell it that, hey, go back there and recompile this thing, make P3 name.o, look up the new constant names here, and incorporate them into the code. So there's no way for it to know on its own that P3.h somehow affects what's going on in P3.o. It certainly would know that P3 name.c affects what's going on there. But we have to tell it about other things. And when it has a .o thing here, notice there's no rule given here at all for what to do. Well, there's a default rule for these guys, and that is basically to run whatever you had in the CC command. So it's going to do $, whatever it found in CC, which for us was GCC. And it's going to use $C flags. So it's going to say GCC, remember it was -O, Q3, and we had a -G, and all sorts of other stuff here. And it knows, again, if we're making name.o, what I'm compiling out here is name.c. So it can work out all of that stuff for us without us even having to say anything like that on this line. So there's a bunch of implied dependencies. So if you go through and change P3 name.c, well, and then do a make here, it's going to discover, oh, that's a newer timestamp from this, so I'm going to recompile it using something like this. And then since this guy now has a newer timestamp from P3, I'm going to remake the P3 to get our new A.out file. And if my original goal is to run test, once I have that code made, then I can actually run the code and get them forever. So if you wanted to just create the P3 guy without running that test, you would say make P3. And you give it any one of these targets to make. Right? But if you just say make without anything, then it just goes to the first target in the file, and that's the one you're going to run. Right, so those are the rules for make. And notice you can do some things like this here. We have a make clean, which, like when I had this one, it created a file called P3. When I had this, it created a P3 name.o, and so on. You'd think this guy is going to create a file called clean, but it's just going to do whatever commands you told it to do. And in this case, it doesn't make a file called clean. It instead cleans up your directory. It gets rid of all the stale, not old files, gets rid of your binary, so you're back to your normal source code with nothing already precompiled at all. I don't know if you start from scratch, but all right. So most make files have a clean thing here, but they don't have to have one. But it's something that people tend to expect to have. You would forcibly remove all the other stuff that would have gotten made when you created this file and go back to your base source file. All right. Now, notice that if we did not change, say, Q3 helper.c, but only change Q3 name.o, we would discover that, hey, this .o file is fine. It's got a timestamp younger than the .c file, so I'm going to leave that alone. But if this one wasn't younger than Q3 name.c, it'll recompile that one, and then it will put the two guys together. The old one, which hadn't changed, and the one it just created, to create the new P3. So we don't just always do everything all over again when we type on hey. Those of the modules are already up to date, fine, we just leave them alone. And sometimes Make will tell you that everything's up to date. Nothing needs to be done. So if you type Make twice in a row, probably nothing will happen. All right, we're definitely going to make use of that in building the kernel. Because there are thousands of these .c files that we have to create. And if I make one little tweak somewhere, I don't want to have to review all the thousands of them. I just want to review the parts that depended on that one little change. So make files are very, very nice. All right, questions about how Make does its thing? No, it will. If you don't have the -f, it'll still get rid of these guys. Unless they would say read-only files, and then it's going to probably say, hey, you really want to get rid of this? You didn't give me the right permission, so I don't really want to remove it. -f said remove it anyway. And also, if T3 wasn't there, maybe these .o files were there, but that wasn't, and you just said rn those three guys, well, it could remove that, it's happy, remove that, it's happy, but it couldn't find this one, so you get a complaint that says, I can't find it. With the -f option, it just complains about it and it's just going to do it. So that's why we put the -f. It's pretty much what we want. Remember, there's a really dangerous one, -rf, which means recursively you remove things. If you've got a directory here, get rid of that directory and everything below it, and don't stop for nothing, just get rid of everything. As root, you can really screw up your system. So be careful when you're typing those commands as root. If you're making sweeping changes with the -rf. Right, I think we have a good question. Right, let's see how we use that. And you may recall in C2WM there, you have an xmake nknf file here, and xmake the make file, which gives you instructions for first constructing the make file, which contains the instructions for making C2WM. So we go through a similar set of things of all the bootstraps here in making the kernels. So there are some targets already in this make file, but things that's mostly going to guide the installation about what happens, what modules get created, what parameters we put in, is based on this config file. We probably don't have one of those based on. You could look over this make file a little bit, find out what its first target is, what's going to happen to this type of make, for example. But there's lots and lots of different targets in there, and we're going to use a whole bunch of them during this level. All right. So if we need a .config file, one of the good ways to do that is get the one out of your running kernel. There is a proc directory there on most Unix systems here, which looks like it's a directory with stuff under it, but it's really kind of a fake thing. It's giving you some window onto the kernel. Let's look at /proc. And what you have there are a whole bunch of directories, which are grouped, and these are various process IDs of currently running processes. And if the process dies, the whole directory structure will leak out. It's not really a directory there, etc. This is just stuff that the kernel knows. It's data structures in the kernel presented as though it's in a file system for you to easily be able to look at. Let's see what our kernel is here. It's, I'm sorry, our shell is, it's 19983. So we're going to CD down into proc 19983. All right, let's do an ls-l and see what we have there. A whole bunch of files. Not that I logged on as NAS100 here, so not too surprisingly, these files appear to be owned by NAS100. That's the name of this particular process. And there are various things in here, the status of the system here, etc. You can go down further and further and here to find your map to the various pages you have in memory and whatever. all that stuff is available. Now, underneath proc here is not just a data structure like this about every single running process. There's also things about the kernel itself, the different little groups that there are in the kernel. And indeed, if you're root, you can go in there and go into one particular one of these files and overwrite it with a new value. So there might be some kernel parameter that's currently 0, and this one will show up as a 0. And you can tweak it on the fly by just overriding that thing with a new number that you want in there, and a non-zero value, and your kernel will be a little different. Usually there's system calls and whatever that you can do this, a little less obtusely to get the effect that you want. But you actually can change things about your process that way and about the kernel. So that's the sort of stuff that's underneath that proc directory, and sometimes go around and you can see a bit how that works. All right, so underneath proc, at least for a Linux system, probably not for a Solaris system, but if you want to enter this, you'll probably find a file like this in the config file that's for the CentOS system on your machine that you just got to have. So there's one of these config guys here, the .gz, indicates it's been GNU zipped to. There's no point wasting a lot of RAM space here. When, as you'll see, a lot of the lines in that file are very, very much the same. We may as well compress that and emphasize that what we actually need to do. So you can see that that is basically just a compressed file, and if you look at some of the things in there, you could do a normal war command would just show you gibberish because it's compressed stuff. And zmor says, hey, uncompress this guy and now show it to the game face. So you get to see some of the things that Right, so you could basically do this and overwrite the config file, or you could go and just say make clone config. And if you want, look that up in the make file, and I'm pretty sure what it does is it does a zero on this thing and redirects it to the config file. So it's what we could have done. Alright, now that's the config file we're going to start with, but we're going to make multiple changes over the next few lab things. So let's get that guy checked in first. So we're down in this particular directory, and CD uses source Linux, but that was a soft link. Where you really are is in someplace like this. So that's the config file that you can check, and then make yourself on CS the rest of it to do. So you can do a word count on that thing, and it's probably something like 6,000 lines or so the last time that I had looked, and it keeps growing every year, of course, and they have more and more stuff. They have video support, and every time somebody brings out a new device, like that keyspan thing, we make provisions in the kernel to be able to handle that device, so the thing just gets bigger and bigger and bigger, and it's now it is quite large. Every piece of software, of hardware that they've been able to figure out how to do under Linux. And many companies don't cooperate with that. Like they make their drivers for Windows, and that's it. So it's up to people to sort of deduce what might be going on inside your graphics card or whatever, and come up with a decent driver that will work under Linux. More and more companies are getting to where they're playing nice with Linux, and it's taking over larger user space. So a few people are willing to give you their good drivers. Now, the companies like the graphics companies really want to give away all their secrets, so often you don't get to compile all the source code. You don't really see their source code, but they'll make drivers available to you, which you can then add on to your system. So if you are putting links on your machine at home, figure out what kind of graphics card you've got, and if you're lucky, if it's ATI and NVIDIA or whatever, do have Linux drivers for them, and you can get their packages and wind up using those drivers, and then things work a whole lot better because they're really configured for the hardware that you actually got. So those generic Unix drivers, but to get the best behavior out of it, get the things, it's just again some graphics card manufacturers are not releasing that information to the Unix community because the Windows drivers use it. That's more important. Definitely worth your while to make that really specific. Now, under Mint, somewhere in your control center is something where you will look for proprietary drivers and things like that and tell you what's available, and then all you have to do is click a button and pull down your machine and install it. So it's in many cases quite easy to do. All right. All right, now we have something that sort of came off of what was on the list there. We sort of clean this up a little bit. There's various different obtuse targets that we need to use to get this to work out right. But these things in the order suggested here that everything will indeed work. So we're going to go make and mark proper to begin with here. And then we're going to take a root config dash and whatever our unit thing is here with some long string of digits and stuff. We're going to copy that into this config file. So this will make up something that's appropriate for whatever we're running right now. And then we'll take a whole bunch of these config files here, and we'll make this particular one and stick it in the config file. All right, and when we do this, we have a backport here and a backport there. We want to look up the result of union-r and pretend we have typed that string of digits there. Digits dashes. Yes. All right. Now, if we want to make things be different than what we've got in the current kernel here, we need to change that configuration file. And there's various ways to do that. Here's essentially the old way, back when it wasn't 6,000 line file. There was maybe 100 or 200 lines. You did a make config, and it would ask you line by line. You want to set this parameter, and I set that parameter. And they have defaults for each of these. You get one for each thing that you want. So until you get to the section you want to do this parameter. But if some reason they try to do that 6,000 times, so people tend to not use that much. But that was the original config thing. And it made sense when we had a much smaller configuration file. It was much less complicated. Unix was capable of doing. Alright. Alright, so just to give you an idea of what's going on in here, basically you have something like this. A line will come up, and it's based on a line in that config file here. Let me ask you a question now. Maybe you've prompt for those development that you can do code drivers and let us know about that. And the guy in capitals here is what's going to be the default if you just hit enter. Like yes. But you can type in if you want, or you can type a question mark and get some idea of what the configuration actually is. And it'll give you a paragraph about what they're asking you. And so you can make a more informed decision. Alright. So what's currently in the file, the reason why they have that capital Y there is because in the config file there's a line that goes like that. Config experimental is set to Y by default, and you're saying that you want to keep this default or you want to change it. And furthermore, they have one that comes down here. You want to append version information to the version stream. And here the default was no, but you could change it to yes if you wanted that to happen. That was a line in the file that essentially went like this. And notice it's really a comment. Before it actually starts doing this stuff, it strips out all those comments. But you can infer that this was the default here, is to not have that set. So you don't have to say explicitly config local group is not on equals n. That's what you're going to get if you just don't mention it at all. It speeds up the problem. But it keeps all that information in the config file so that humans have an idea of what's there, and more importantly, what's not there. So there's common lines that you can use that. All right. So again, you don't want to do that forever, so you can go see or something and get out. All right, now another one that's a little more friendly is the menu config in here, and that will break things up into a two-like structure. You have a choice between going for disk drive things or USB system or whatever. And again, you can work your way through the sort of graphical interface here. But still, you don't you can do this on an isolated control terminal. Move over to this one column down here. You mess with the gas stuff on the system here. You've seen this sort of thing in practice. Or if you're in the days back in MS-DOS, where you have to use that. Just basically have it. Alright, so you can move around with that. And again, just experiment with a little bit as you do, and then exit out. Tab to the place and the exit highlight. Alright, now if you've got X up and running, there's much cooler interface where you can now use your mouse or whatever to move around rather than having to use the arrow keys. So you can do a make of X config. And that should work for you unless you left out this particular package. But again, if you follow the Lab8 and save for it, it should be there and available for you. If not, this is basically what you need to look at. The Suzy grab and put those back in. So again, you can take your mouse and kind of look around for various things. You can find that keyspan stuff here. The screen is higher. So that would be down on the device drivers. We kind of got a clue about that, right? When we were looking at where things lived, when we were inserting the modules, the drivers, what kind of drivers, USB drivers, what kind of USB drivers, the serial ones, and so on. All right, now you can get out and give you an opportunity to save anything you might have messed up, but again, you can save it. All right, and then the other way that you can change this config file, since it is a readable text file, is you just edit it. You append it with VI, and do a slash and look for this thing here, which is part of that. And look for this guy here that says, hey, this serial keyspan stuff is set up to be a module that gets rerun. Now we could change that. We could say, hey, build a new kernel so it's always there and always loaded with a yes here. We could say, hey, build these modules with a no here. But here we have the option, when we need it, we'll bring it in. So it's taking up a little bit of disk space, but unless we're actually using that device, it's not taking up any RAM. That's a pretty good trick. Most of the things in the kernel are indeed not good. But what we'll do to it is basically turn it off. Make it a comment rather than something that actually got set. All right. As you're searching through here, there's about 12 other lines, I think, that involve ways to configure this particular keyspan guide here if you were going to create a module. As it turns out, you don't really have to go through and comment all of those guys on it. When you're not making a module, one of these, I forget which one, these two guys here, is going to rationalize the thing and not talk about the option for something that doesn't exist. So you really only have to comment about that in one line to make that go away. All right. So make the whole config. Do that, it's going to take your config file that you've got and rationalize it. If you look again with VI, those lines will not be there in the X values. The 12 guys that will not be and then we can set things up, and we can make a whole bunch of other make files in various subdirectories along the way to deliver the work. So this will rationalize everything that we really kind of have in and get stuff out. All right. we want to keep the old kernel because we know that one boots. And since we're using pretty much the same, we're in the same directory here for this kernel, if we just build a new one normally, it's going to overwrite the old one. So I want to give this new guy a new name. And I'm going to change it because we're going in here, look at the full local version. It's probably going to say something that ends in this. And you're going to change it with that. Rather than default, you're going to go to CS470. So that way we'll be able to identify a different Linux kernel, a different system map, a different initial RAM disk, etc. That will relate this new thing that we're about to do. Alright, now do be careful. If you do that and you run that old config again, it's going to erase this and put this back. So you're going to come back here and run that again. So at some point you can back up a little bit and make sure you go through the steps and make it recorded. Otherwise, you have to write it. All right. Now, let's see. Next, we're going to do BI again. Get to that line. We could just do BI and then slash and find that. We're going to do plus slash, so go to the first line that happens to have those words somewhere on there. And if it says that it's turned on, we want it to be turned on. So notice I didn't use a caret sign there because the C probably isn't the first character in the line. So make sure it says this. So how about that? Turned on. We've had some problems in compiling things if we've got that same old systems that ain't really good run out of memory. Maybe okay with the new machines that we've got, but if we can say it, let's turn that off. We don't need to repair much of that. Alright. Okay, now we should see the various changes we made. Right? We saved that original config file and all this stuff happened here. We get basically a standard format of everything, even though what we did up here was just put a pound sign in front of this. What you're seeing now is config USB pound, config USB $2 is not set. That's the standard phrase that it uses here. So it's turned your edits into the standard thing that it expects to receive. Alright, so having made those changes, that's a good place to check in yet another version. Step 22 of the lab is where we are. Alright, so now we're about ready to compile a few thousand .c files to create a new kernel image. So that's not going to happen very fast. So we want to basically get it started up, and then we can go on and work on our CWM stuff while this thing jumps around. If you've got X up and running, you can have it compiled all in one window and over in another big window. You can look at this step 30, to do some related things for the lab. Right. Now, assuming you're running bash at this point, particular shell, that you do an S root and a T root, and then you're using TCSA syntax, which should go like this. But what we've done here, and I suggest you do the exec bash before you go back. And we're going to tell it, hey, make this easy image here, so a particular type of compressed image of the kernel. And there is, of course, somewhere in the make file a line that says easy image colon, it says that it depends on the result. And that's going to line by line tell you the compilations and stuff that are going past. We're going to type that into a file so I can see that, what happened when we did this compilation. So what we really want to do is type it into the make.bg image stream. Again, it's just a name that I made up. Didn't really go the same name, so I can find it. So it's going to be food, and when you look at food, you find this. Give it that name now for food. Now, if we just did that, we'd see absolutely nothing on the screen. Because all the output is, if I did greater than and send it into that, all the output would be going on the load. into that file, not on the screen. But in this case, we're typing it to the T command, TE. And this means it's going to send stuff into two different places. Some stuff is still going to come to the screen, but an exact copy of all those characters is also going into that file. That's what T does. Think of it as type thing. We have the output of one guy going into the other, and then we've got a right angle turn here, and we're going in two different places, into this thing and also into the file. Now with with bash syntax, it's saying here, take file descriptor 2, which is standard error, and write that also to file descriptor 1. So all the stuff that would normally be still coming to just the screen rather than mapping, we're telling it to put those standard out and standard error into this file, as well as letting it come to the screen. So you say that differently if you had QCSA. Rather than just depend on type symbol, you type ampersand. So that says some standard out and standard error into the next utility, which has to be the T utility. Alright, so several thousand lines after that, it's going to chug along, and eventually it'll say, hey, this thing that I just created is ready to go. So that's what we'll be looking for out of the corner of your eye when you're watching these things go. But eventually, all that stuff will stop moving, and hopefully you have something like that near the end of the Alright, if you watch what's happening here, most of the time it's going to be CC compiling some .c file, and CC compiling another .c file, and another one, all the way down the line. Every now and then you'll see the assembly getting called, the AF stack. There's a few things you have to do in creating a kernel here that you can't say and see very well. Right? Particularly when you're doing a context change from running one process to now suddenly running a different process. That's a complicated thing to do. There's special machine code instructions to allow that to happen, and there's no corresponding C instructions. So, tiny little pieces of the kernel, really important pieces, have to be written in the assembly. But the nice thing about Linux is it's quite easy to port to a new system because most of the .c files are ready to go. They're almost exactly the same thing. Maybe a few architecture things that you have to do. But the main thing you have to do to get a Linux kernel on a new piece of architecture is to change that assembly stuff about how they do their context. Alright, so that gets you the kernel itself, and not any of the modules. So something will take probably at least a long amount of time is to make all the modules. Alright, now here we'll see another way to save the results in the file and also allow you to see it on the screen. So we'll do our normal thing here, we'll do greater than, and put all the results into there, and also send stuff from standard error on the standard out. So in the error messages that come along also go into that file. So at that point you'll see absolutely nothing. And you can look at that file. Okay, we said tail of that file, I can do that over and over again. We'll see what the current last going on is over there. And tail, that's a -F option too. So it continuously looks at what's in that file. Now it's going to take a while to type that, so you probably missed lines. But you just kind of want to see progress being made. So do this, put it in the background, and you'll really be seeing what's going into that file as it happens. And eventually that will stop, and we'll stop seeing that. So when that happens, then you don't kill this event. You're kind of done with changes to that file. So you put it back in the foreground, and you'll see what the issue of killing it, and once you figure out what to do with it. And there's no need to keep that around. Alright, so we get into some here a long time to build every single one of those modules for the kernel that you set up. It's a whole lot like the old one, but the difference is that you do all of these guys. And then later, in the next lab, we're going to make one more tweak, and we're going to put back those two stamps. And then when we tell it to make those modules, it's going to be going down and you can use subdirecting and saying, hey, everything's up to date too. Everything's up to date too. Everything's up to date too. It's only when it gets down to that USB subsection that it discovers that there's some new things to be made. And then it'll make just those few things and be done. So the second time around, it's going to go a whole lot faster because it's only anything you need to compile it. So right now, it's all new. Alright, now when we did the kernel build, we had a whole bunch of .O modules, and at the end, when we were putting them all together into that BZ image file, where the actual kernel that was supposed to get loaded into memory. The difference here is we don't do that very last step. We make a bunch of these .O modules, Halo modules, kernel modules, but we're not trying to put them all together. And the point of these guys is that they get attached on the fly, like we saw with the two-stamp thing earlier on, just when we need. Right, so they're separate pieces that aren't put together by the way. They get dynamically loaded and when needed. Now, unfortunately, in Bash, you don't get a notification that a background job is done. So that's one of the places that CCSH is a really good shell to use if you're doing things at the keyboard. And Bash is really the best one to use when you're making shell scripts. Because it gives you much more control. But Bash isn't quite as nice as far as giving you notifications. When you have a background job being completed, you get to hear about it right away, rather than to wait for till the end of the commit. I can do something like let's sleep 10 seconds, and I can put that, let's do a control Z here. That suspends it. No matter how much time goes by, we're not going to get through those 10 seconds. I have this guy in suspended animation now. Sleep command is asleep. But I can put it in the background. And then it, I usually do things like the time. And then when it quits, it'll tell me that. So that really will show where I want it. I'm not going to touch the keyboard, but oh, I guess I got my background on the piano. I want to get it back. When it gets done, it finishes. Do the same thing again. Put it in the background. I've got a prompt here. That guy is in the background. And now after 5 seconds goes by, we get to see that thing without me having to touch the keyboard. In Bash, you would not see that at this point. It's going to have to be after you type some new command and hit enter. Then you'll get to see that some previous guy is on the table. So TCSH is actually a little bit more convenient for doing this part of the line. But I haven't used Bash for some syntax. Okay. All right. Now, there's an easy way to install the kernels and modules here. There's a nice little target for that. And then when you do that, it's going to overwrite the stuff in the node that works. So what do we want to do that? So we'll put the modules in because that doesn't work to the same way. But the actual kernel itself, when you do that by hand, also gives me talk about how where all these things go and how it actually is consistent with that. Okay. Alright, so I'm fine to just use that command if the terminal rebooting is perfect and it's working and so on. But what if it's broken somehow? Then I've overwritten my own kernel and it's screwed. So what we're going to do is put it in this Alright. Yeah, the modules do get installed in a completely different place. I'm going to go into the user lib something or use a subdirectory name for a new kernel. So we can do a make the modules install without getting us into play. Alright, and of course you're going to take a while to copying all sorts of these kernel objects into the appropriate directory structure and creating new subdirectories as we go to the go ahead and do that particular name. But we're not going to do the corresponding one to change things in /boot. Instead, we're going to do that Alright, so here's what it takes to do the kernel, or the part of this component, all of it, in /boot, as we saw pretty early on here, there was various Linux files and stuff like that. So we're going to take this thing that had just gotten made for us. This is our first target that we made for libraries, thousands and thousands of .c files to create that DB. And so what we're going to do is copy it here, preserve the dates and so on here, and overwrite something that's already there. I put the -F option there. And the -I says require, in case you're about to overwrite something, -F says boot. So we're going to take that file, the one that we just made, and give it this new name. And I don't recall whether what's on the DVD is this particular sequence here, but I think the same sequence that we had on the DVD, same numbers we used earlier on. And so give it that name, but instead of -default out here, give it our new name that we have here, so you can tell the kernel's default. There's a guy that looks like that, -default. You're going to take this new guy and call it almost the same name, but with -47. Okay. Alright, now what numbers we actually use there? As it turns out, there's like 3 different versions of these strings of numbers. When we did that, this version string came up like this, with a .1. Now, if you look at that directory under user source, it doesn't have the .1. That's just that portion. And if you look at the directory name for where the modules have gone, it was lib modules, this amount of stuff with the -3, that's CS470. And so maybe we should have that .1 or the -CS470, or perhaps nothing. Which one are we supposed to use here? Basically, you want it to match whatever we have with our lib module. So the string that they were using there is the one you want to use in that. Alright, so then what that thing is the compressed version of the actual kernel, the thing that's going to get loaded into RAM, but to say this basically is compressed. So what happens when you boot your machine, our startup program figures out where the blocks that hold that file live, and it's got its own little uncompression algorithm in there to expand it out, and it puts it into the appropriate places in memory. And then it's going to control what we're going to for that new program that is there. And of course, this has to be tailored for where the hardware is. Alright, so that's one of the things that we need. We also need a system map. So it has created one for us underneath that directory. And we're copying that and giving it this new similar name to what we have for the other. So what's that thing look like? Well, that's this is the last paragraph, I guess. It's a long paragraph. 35 seconds here. So let me stop there for today. Just take up what the system map is about next time.